some theory here. So we're talking about water in pipes when we're talking about hammer. So hammer is dealing with pressurized flow. And normally, when you're modeling a system like that in, say, WaterCAD or WaterGems, basically the water is incompressible. When you have an EPS that you're simulating, when you go from one time step to the next, things are happening instantly. You don't see any transient effects because the water is assumed to be basically incompressible. But when we're talking about hammer and what happens between those steady state periods, we really have to consider that water is slightly compressible, and because it's very, very heavy, that's why you can have very significant changes in pressure when suddenly the momentum of all that weight is stopped. So it has to be released somehow. And due to the effect of line packing, where you have water molecules that are very slightly compressible, they can pack up against each other and release that energy when you have that sudden change in momentum. So again, little compression releases a big pressure surge. Those waves travel very fast. And again, friction is what you need to dissipate the transient energy. So without flow, you will either take a long time to dissipate that energy, or you never will, at least in a theoretical model. And there is something called the transient friction method, which you can use in hammer to basically identify how friction factors are treated during the transient simulation, so that as the hydraulic conditions are changing significantly during a transient event, the friction factors, the theory tells us that they actually change slightly. So if we're dealing with the Darcy-Weisbach method, the Darcy-Weisbach F may not necessarily be a constant. So by default, we assume that it is. But if you want to say that, well, that friction factor can change as conditions change, which can actually have an impact on, when you're dealing with situations where you want to see how many cycles it takes for it to dissipate, you may consider using the unsteady friction method, which I can show you in the product. Another point, fundamentals here. So air or vapor pocket collapse often governs, so this is very important. So if you neglect this, it could be a serious problem. If you're only looking at the impact of the pressure wave that results from a pump shutting down or a valve closing, and you don't consider air valves or having accurate elevations to simulate vapor pockets, you could be missing out on some very significant transient events. We're going to get to that in a moment. And because of that, and because of how significant the effects of air or vapor in the system are, they can often govern decisions as far as mitigation of transients. Last point is that local causes and flow surge controls can have global effects. So even if you're changing something or something is happening on one side of a system, that can have an impact on a larger section of your system because of the way that waves will propagate down and reflect, and how things can interact. So something to consider there. So on the point of wave propagation and reflection, so again, rapid changes in velocity or pressure can cause a transient pressure wave, but we're really talking about rapid changes in momentum, which is mainly velocity of the water column moving. The waves travel to every part of the pressurized system. They can, split off if you have a flow split or a lateral pipe going to something else. They travel down every part. They can bounce back, and the timing of those waves can cancel out another wave. It's a very complicated interaction there. So I'm going to skip ahead here. So when it comes to velocity, well, what velocity is okay? There really isn't any safe velocity, and especially when you're talking about high velocities, which maybe you want that for being able to flush your system to make sure there's no sediments. But when it comes to transients, if you have a very high velocity, then if that velocity stops very quickly, you're going to have that much higher of a transient event. But even low velocities may not necessarily be safe because lots of different complicated factors, because you could have a change in velocity in a different part of the system that then reflects and propagates down the pipe, and maybe it reaches a section where the velocity is not as fast. It can still experience a significant transient effect, even if the velocity is low, and especially if the pressure is low. The lower your initial pressure, the bigger the risk is that your transient minimum pressure will be a problem. Might be subatmospheric. So during a transient, it might result in column separation. And when we say column separation, we're referring to vapor forming when the pressure drops below the vapor limit of water. So I'll talk about this in a little bit, but basically you have a change in phase where the water is boiling, and that separates the two adjacent water columns, and we call that column separation. And once the pressure returns, those two water columns come back together, and it's like a head-on collision when that happens, because you're considering the relative velocity of those two water columns as they hit. So that can cause a big upsurge pressure when the vapor pocket collapses. Okay, pressure consideration. Again, no pressure is really safe. If your pressure is initially low, then that much higher chance that it will possibly drop below the vapor pressure limit during your transient event. Also, if your initial pressure is high, well then, you're probably more at risk for damaging the pipes and exceeding the pressure rating. You also have to consider the force that these transients have on the actual, the joints of the pipes and the anchors and things. It can actually shift things around and shake the system. So hammer can actually do a force analysis as well. Your effective diameter will be impacted by corrosion and tuberculation and things like that. So the actual effective diameter that flow is going through could be significantly different, which the point in the slide is that that means that the velocity the area is different, and thus the velocity is different. And because with a transient we're talking about change in velocity is the main impact. The change in momentum from that velocity is the main factor in the the impact of a surge event. So if there's an error in that area, then it could result in a pretty significant error in the transient results. So if you had assumed that it was the full diameter, you might be seeing a much higher velocity and maybe a much higher surge. Your transient results may be very different. Now, obviously, if the pipe is very old, it may have other problems. There might be leaks, or it might the effective pressure rating, the pressure above which it would burst or be significantly damaged, may also be impacted. So that's another consideration. If you know that a pipe is decreased by a certain amount because of tuberculation or corrosion or whatever, then you want to enter for your diameter the effective diameter that the flow is actually traveling through, to get an accurate velocity and thus accurate transient results. So the point there is the diameter in hammer is the inside diameter. So pressure wave speed calculation. So how fast a pressure wave travels in a pipe. There's an equation here that you see in the bottom of the slide, and that's basically what hammer uses in a little tool called the wave speed calculator. So if you don't know the exact wave speed in like meters per second or feet per second, you can use this little tool. So based on some liquid and material properties and whether it's supported at one end and this and that thickness, it follows this equation and will apply the calculated wave speed to all the pipes in your model. So it's a handy little tool there. So getting back to characteristic time, so we talked about how a transient event, a hydraulic transient that you would consider something to analyze, is an event that occurs faster than your characteristic time. So every system has this characteristic time, and it's a function of the length of the longest possible path from where the transient is occurring, down to the end of the system. Okay, so basically, your wave speed is going to be on the order of could be something like 300 meters per second, 1400, which is about 1,000 to 4,500 feet per second. It's really a function of the not only the what fluid is going through it, but also the sort of elasticity of the material. So a PVC pipe will have a different wave speed than a ductile iron pipe, and that can be significant because it impacts how fast those waves travel, which impacts when they reflect and when they combine with other waves. So it can have a significant impact. And again, if you're ever unsure, and even using the wave speed calculator, try sensitivity analysis. Try both ends of the spectrum. See the impact of the transient simulation. The results that you get from a transient analysis. If they don't change very much, then you don't have to worry about it. If there's a significant difference, then you do have to look into it and consider either a conservative estimate or get something more accurate. So system response to change. So again, if we compare something that a change of some sort, like a valve closure, to the characteristic time, if it's that change happens, that change happens instantly, then that's an instantaneous change, and that's something that you may want to look into. Okay, so I'm basically talking about this slide about response to change. So if the change is instantaneous, well then obviously it's going to be less than the characteristic time. If it's generally between 0 and the characteristic time, that's what we would refer to as rapid, and we want to look at that using hammer. If it's greater than the characteristic time, then it's more of a gradual event, and you could probably solve that by hand or through standard rigid column theory. And if it's much larger than the characteristic time, well, that's probably a very slow event, and you could even get by just doing an EPS, which is an extended period simulation, where you're just looking at snapshots in time, basically instantaneous change between one steady state simulation to the other. In other words, you may not need to do a transient simulation if it's happening that slow. Now, when we refer to elastic theory versus rigid column theory, we're going to talk about that a little bit, but Hammer is always using the elastic theory as far as calculating transients. So rigid column theory is a faster method to solve, and definitely suitable for things that are happening more slowly. You can basically use it to track the length of an air pocket, a local high point, and some other things. But the elastic theory is a little bit more complicated. It's a little more numerically intensive, and that's what Hammer uses by default, because all computers are very fast now, so there's no reason to go with a slower method that could give you less accurate results when you could wait fractions of a second more using the elastic theory and get better results. So if we do a comparison here, you can see that the faster you close a valve, the bigger the head on it, the more elastic effects can become important. Whereas if it's more of a slower action, then those elastic effects are not quite as significant. But Hammer uses it by default, the elastic theory. So no matter how fast or slow something is happening, it's using the elastic method. So if you move on the x-axis here to the right, you're taking longer to close the valve, and the error in approximating to rigid, it's small, so it doesn't really matter in most cases. Bottom line is, we use the elastic theory, and it tends to be more accurate, and it might take a little bit longer to compute, but we're not talking about very much for modern computers. So here we have a little example profile where the sort of dark dashed line here, if you can see my cursor, is the theoretical maximum head. This is a pump shutdown event here. So this dark dashed line is the theoretical maximum head if we solve the rigid column theory, whereas the blue line here is the maximum transient head if we solve the elastic theory. And you can see if it's more of a curved line, but it is higher, at least out to as long as this profile is here. So conversely, when we're talking about the minimum head, again, it's more of a straight line here with the rigid column theory. But for elastic theory, it's a more severe, more conservative, and more of a sort of a curved line here. So I'm going to do a little demo here. Back to Hammer. This is the second sample file that's also included with Hammer. It's sample 2, so I should still be sharing here. This is a simple case just like we just saw here with a pump shutdown. And the key point for that that we're going to take a look at here is that in this case, the waves that result in the transient event, the pump shutdown, will be attenuated this time because we have friction effects. And the water in each of the pipe segments is going to flow differently because of the topology, which you'll see. So let me switch back here. So I believe I've already calculated this one, and we're going to take a look. So again, this is a pump shutdown, and it is shutting down right at the very first time step. So I'll make this profile pretty big here for you to see. So the pump is on the left side, and it's pumping up to a reservoir on the right. So you can see that the black line here is our initial hydraulic grade, and the red line is the the maximum pressure that maximum head that occurs over the transient simulation, and the blue line is the minimum head that occurs. And we usually refer to the difference between these two as the transient envelope. So if you hear that term, that's what we're talking about. So if we start the animation, we can see right at the first time step, we get what you might refer to as a downsurge. So the pump was pumping at a certain rate. You have a starting steady state simulation, a starting steady state condition. Now suddenly there's a power outage or some emergency condition happens. The pump shuts down, and we're then transitioning to a final steady state where the pump is off and there's no flow through the pipeline. So when we first start that, we see this downsurge wave propagate down the right side to the end of the system, and that's a reservoir, so it bounces back a certain way, and you can see it reflect back, and then it reaches the pump and then reflects back again and reaches the reservoir and reflects. So if I fast forward a little bit here, we can see eventually it settles down because we have the transients dampening from friction. And it's kind of hard to see here, but it's basically a straight line instead of a sloped line, because we're transitioning from positive flow to zero flow. And if I take a look at a graph view of this, let's take a look at the pressure and flow just downstream of the pump. So we can see over the course of about 30 seconds, the flow takes quite a bit of time here. Let me see here. So what we've got here, in fact, if I extend this out a little bit longer, I'm going to show you what happens if we have a longer duration so we can see a little bit more. It's not just 30 seconds. Okay, so the way they have this set up is that basically they have user-entered initial conditions, which means that it's not using a steady state simulation here to establish that starting steady state. It's actually using some user-entered values. So if you happen to be looking at this model yourself, you'll see that this is, it's set up this way. So we can actually switch it to use computed initial conditions, and I'll show you how to take a look at those. This will also be covered in the workshops, but we'll touch on that quickly here. So we can see this is your initial conditions profile. So we have a slope to our hydraulic grade because we're pumping from the left side to the right side. The pump is adding energy, and there's a friction slope as it reaches the final reservoir. And if I do a transient simulation and take a look again at the profile there, we can see in this case pump shuts down and it eventually reaches here you can see it better, it's more of a flat line, and in fact it's a little bit sloped to the left, which is because of the slope of this profile here, which is the green line. So you can see that the physical profile of the pipe is sloping uphill. So when we shut the pump down, if there's no check valve in the pump, then eventually the flow will reverse. So what we have here in our final steady state is flow that's going in reverse a little bit. And I'll try to open this at the same time as a graph so you can see. And I'll graph the hydraulic grade and flow through the pump. Okay, so it's a little easier to see here. So it looks a little funny on the flow scale because of the orientation of the pipe. So just ignore the sign in front of the value here for a moment. So basically, we had a positive flow through the pump initially, and you can almost imagine this line in reverse. So what's happening is, suddenly we had this pump shut down. So we see a relatively fast drop in pressure. This is your downsurge, and eventually the pump flow reaches a final steady flow, which is actually in the positive. So think of this as this is the negative. This is the reverse flow. So the pump shuts down, and eventually that water column reverses. And so when we're out to about 100 or so seconds, you can see we've reached our final steady state because those waves were able to dampen out because we have that reverse flow, and we've reached our final steady state, which if you look at from a head perspective, you can see right here the initial head about 165, and the ending head is just a little bit lower than that. So, if we were to just ignore the transient effects and just run an extended period simulation and say WaterCat or WaterGems, you would see one time step is 165, the next time step is 158 or so, but you're missing out on this transient that occurs in between. So that's what sort of the point of this is showing, is that when you introduce friction effects, you can see more clearly that transition from one steady state period to another. All right, so getting back to the transient theory. So key points, again, wave propagation attenuates with friction. It reduces over time. The water in each segment slows differently. You have that sort of curved hydraulic grade envelope, and that's kind of showing that elastic effects. Now, what if the pressure dropped lower than the pipeline elevation, which didn't occur here, but we did have a bit of a knee in the system, and I'll switch back to hammer to kind of show you that. So if we're looking at the profile here, we have a bit of a knee occurring here. If subatmospheric pressure were to occur at the knee, then you could be at risk for water column separation. But that doesn't happen here. We can see the blue line, our minimum head, has never dropped below the physical elevation of the pipe here. So we're not at risk, at least in this simulation, for problems with low pressure. And that's mainly because it's pretty well uphill. There's no intermediate high points along the way. In our right at the end, it's going swiftly uphill. But you can imagine if this pipeline had a little hill in the middle, that could be a significant problem.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.